Hi again, students. This is an optional video that you do not have to watch if you don't want to. I'm not going to be testing you over this algorithm that we're learning, and I've gotten smarter since that first video. I now have 2 pages showing at the same time. So we're starting on this page, which is page 47 in your worksheets. Completely optional. Again, you do not have to learn this algorithm, but I think it's kind of interesting, so maybe you just want to learn it. I have another little silly thing I talk about when I try to teach this algorithm, and that is dropping bombs and blowing up cities. Now, I know this is not a nice thing to say, but it kind of explains what's happening in this algorithm in a way that people can remember. What we're going to be doing is starting with a machine like this one. Could be deterministic or non-deterministic. It doesn't matter. It'll work on both of them. It's easier on deterministic ones. And we're going to, over time, turn it into a machine that looks like this one on the second page. I know my cursor is so teeny tiny you can't see it. But way down here on the right hand corner of the screen, this area right here, is the finished product of one application of this algorithm. And this is the regular expression that it produced, lambda or A followed by quantity BA starred followed by B. When you look at this machine that we began with, this state down here, state 3, is actually a trap state right here. See, you go there on B from state 1, you go there on A from state 2. It's a non-accept state, and it's once you're there, you're stuck there. You can't ever leave it. So this is a trap. Really, all of this business, let me make sure I'm actually writing. Yes, all of this business can just be erased. And it leaves you with this machine, which clearly accepts the language A, B, quantity starred. Right? A, B, A, B, A, B, A, B, quantity starred. Well, is that the same regular expression as this one over here that I said the algorithm produced? It's certainly not the same, doesn't look the same, but is doing the same thing. They are equivalent regular expressions. I need to fix my size here. They are equivalent regular expressions. Yeah, lambda is allowed. The star in this one over here says you can have lambda if you want to, but over here it's made explicit, lambda or, and then this A and this B have to be there. In between them, you can put BAs if you want to, any number of times. That is doing the exact same thing as if you did AB and then another AB. See, there's the A that has to be there, that one. Here's the B that has to be there. And in between them, you can put BAs. That's what came out of the run of the NFA to REX algorithm this time. This algorithm has an unfortunate characteristic, and that is that depending on the order in which you choose to blow up states, to remove states, the regular expression that you get at the end is different. They're equivalent, but different. If in this run that starts here on this page and goes through this page, we removed state 1 first, you see, and we ended up with this machine over here at the top of this page that only has states 0, 2, and 4, and then we removed state 2. If we had removed state 2 before we removed state 1, then the regular expression that would come out at the end would be the one that we like, the AB quantity starred. And that's the unfortunate part of this algorithm. Depending on the order in which you choose to do things, the regular expression you get out at the end is different. But we have a rule of thumb that if we follow, typically we'll produce the shorter regular expressions. So let me explain this algorithm. First thing we have to do, let me erase this. Whoops, let me just clear this. Okay, first thing we have to do is make sure we have a state that is a start state that nothing comes into. This is a start state, state 1, but B is coming into that state. I want a start state that only has an outgoing edge. I also want an accept state that nothing leaves. And this is an accept state, but unfortunately this A is leaving that accept state. So what I want to do first is add a new start state and a lambda transition to the original start state. So that's what I've done here. I've added state 0 and lambda to state 1, and I made state 1 not be the start state anymore. 0 is the start state. And then I add a new accept state. I did that down here, state 4. I took away the accept status of all of the original accept states. There was only one. It was state 1. It's not an accept state anymore. And I added a lambda transition to the new accept state. So here's my lambda transition down to the new accept state 4. When this algorithm is completely finished, the only remaining edge in the machine will go from the new start state to the new accept state, and there will be a regular expression written on that. So that's the first step. Sometimes your start state is your accept state, and you end up with this kind of wacky thing happening. Now you look around your machine, and if you see, well, first of all, I think I would do number 3 before number 2. Take out any trap states that you see. Just get rid of them. You don't want to incorporate a trap state into your regular expression, because that is how the processing goes astray. What you want is just what keeps the processing good. You want to incorporate all of the good stuff into your regular expression. So you're going to take this out completely, leaving you with just this 0, 1, 2, 4 machine. Now you look around in your machine, and if you had any things that looked like this, where you had, and that was going to the same place, you had one regular expression or letter there and one here, then you could combine those and put an OR between them. We don't have anything like that in this machine, but we'll practice on one that actually uses that. So that was this step number 2. We've done 3 and 2 now. So then we have to begin blowing up states. And the rule of thumb tells us the best order in which to do that. We want to select the least busy state to blow up or to eliminate. Now, what do we mean by busy? Well, what we're going to do, remember, we're not going to try to blow up 0 or 4. We want those at the very end to be the only remaining states. We're going to calculate the busyness ratio by multiplying the number of incoming edges that come in from somewhere else by the number of outgoing edges of a state. So this is 1 times 1. Has one incoming edge, this one, has one outgoing edge, that one, and so that is a busyness quotient of 1. For this state, we have 1, 2 incoming edges that come from other places. This one comes from 0, this one comes from 2, so that's 2 incomings. We also have 2 outgoings. 2 times 2 gives us a busyness quotient of 4. We do not want to do this state 1 first, even though this page shows us what happens when you do state 1 first. It's trying to prove that you should not have done that by showing you what happens at the end. So I'm going to trust that you could read through this and remove state 1 first if you wanted to, but what I'm going to do is try to remove state 2 first. perhaps I shouldn't do this, but I trust that you could read this and go through the algorithm having removed state 1 first. That's what all this is doing. You could read that and follow along. I'm going to remove state 2. So I want to start a new paint with a blank page that we can see. Whoops. We can see. I'll shrink it a little bit so I can. All right. Let me get my other mouse. I'll just drag it right over here so we can see the original machine and the machine I'm going to produce. All right. So here's the idea. Let me just redraw the machine right here so I have the whole thing. So I have state 0, state 1, state 2, and state 4, my accept state. I have a lambda here. I have a lambda here. Those came because I made my new start state, my new accept state. And I have eliminated the trap, and all I have left is that edge A and this edge B. Now I calculate my busyness ratio. This one turned out to be 2 times 2, or 4. This one turned out to be 1 times 1. The rule of thumb says do the least busy first. So here's what I do. I say, oh goody, I get to drop a bomb on this city. Here's my target for the plane to drop the bomb. I draw a little target line around the state that I'm going to blow up. And I notice which are the incoming edges and which are the outgoing edges. Now, just because I'm blowing up this city does not mean that I want to destroy my transportation system. I still want to be able to travel around in the remaining cities, and I've told all the people, of course, to leave this city. It's old and decrepit, and we're going to give them a better life. But in order to do that, they have to move over to this state, and eventually, I don't know, that whole story falls apart. But for right now, what I want to do is rebuild the roads. So I need a bypass. I will need a bypass for each pair of incoming outgoing edges. For this one, I only need one bypass because I have one incoming and one outgoing. My incoming, I make this little doodle when I'm thinking this through. My incoming edge comes from 1 to 2, and my outgoing edge goes from 2 to 1. The label on my incoming edge is A. The label on my outgoing edge is B. So what I need to do is get rid of state 2, but build this bypass. You used to be able to go from 1 and back to 1 through 2, but you won't be able to do that anymore because 2 will be gone. But I need to add this bypass into my remaining map. So I'm going to redraw my machine, leaving out state 2. So I will still have 0. I will still have 1. And I will still have 4. 2 will be gone. I don't want to leave out any of the roads that are already in my transportation network. So I'm going to put in that one. I'm going to put in this one. And now I think about so 2 is gone, and so are the roads that used to connect to 2. This road's gone and this road's gone. They got blown up. But I need to build this bypass that goes from 1 to 1, and so it goes from 1 to 1, and its label is the concatenation of these two things. So its label is AB. And now, to continue, I need to blow up this state. So let me calculate its busyness. You do not use self loops in your busyness quotient. So this still has 1 incoming and 1 outgoing. Don't count this one. It doesn't affect the number of bypasses that you have to build. this time we're going to have an edge from 0 to 1 that's labeled lambda, and an edge from 1 to 4, that's the bypass that I need to build, labeled lambda. I'm pairing up my one incoming with my one outgoing. Up here, my one incoming came from the same place that my one outgoing went, but that's not happening down here. So my little doodle off to the side here shows me that I now need to build a bypass from 0 to 4 labeled, oh, I forgot something. There's a self loop on 1. I got to put that into my doodle, and I got to put that AB on there. If there's a self loop on the state that you're about to blow up, that has to be incorporated into your doodle. Up here, we didn't have that, so we didn't need a bypass on 2. It didn't have a self loop, but we do have that on this case. And so when we redraw our transportation network and we eliminate state 1, because I'm fixing to blow up this state right here. See, I'm blowing that up. But what I have to do is put back into my transportation network this bypass that goes from 0 to 4, and its label is going to be the concatenation of this, which is lambda, with this loopy thing parenthesized and starred, because you can do it a lot, with this. Now, once I concatenate all this, I don't need these lambdas anymore. So look what happens. I build my transportation network, state 0. I'm not going to have 1. I'm blowing that up. Here's state 4. Currently, there is no edge between 0 and 4. My blast is going to take out every road in the whole thing, except for this bypass that I'm building. And the bypass is going to be labeled with the concatenation of lambda, AB star, lambda. You don't need the lambdas because you have more stuff. And so all we really get is AB quantity starred. And that's a much better regular expression than the one that came out when we removed state 1 before we removed state 2. Please follow along with the worksheets so you can see how that happened. Let me just give you a little heads up here. Let me minimize this. So what happened is when you calculated the busyness of state 1, you had 2 incomings. Look up here at this. You had 2 incomings, 1 from 0, 1 from 2. And you had 2 outgoings, 1 to 2 and 1 to 4. You had to pair up each of the incomings with each of the outgoings in your doodle. So here's the doodle that resulted. You had an incoming from 0 and an outgoing to 2. You had to pair those up. You had an incoming from 0 and an outgoing to 4. Then you had an incoming from 2 and an outgoing to 2. And then an incoming from 2 and an outgoing to 4. So you made this doodle. 2 times 2 gives you 4. You have to build 4 bypasses if you want to blow up state 1 first. And your labels to these are lambda A. The lambda goes away, just leaves you A. Lambda lambda, you need a lambda, a single lambda on that bypass. This one will have a BA, and this one will have a B. So then you redraw the machine. We do it over here on this next page. Let's go back to the top. So we're blowing up state 1. Let me go back over here and make sure I'm in red. I'm about to blow up this state. Whoops, I'm supposed to be in red. Okay. Blow up this state down here. Taking out, whoops, not that. That's my target. So I'm taking out this road, any road that the dashed line crosses, I'm blowing up. I'm taking out that road, and I'm taking out that road. All I'm going to have left is state 2 sitting out there with no roads, state 0 with no roads, and state 4. So that's what I had prior to adding in the bypasses, just a 0, a 2, and a 4. Now you look at these bypasses. Your first one goes from 0 to 2, so you draw that in, 0 to 2. Maybe I should be writing in red. And you label it with the concatenation of lambda and A. So that just becomes A on that road right there. That's an A. The next bypass goes from 0 to 4, and it has as its labels 2 lambdas, and so you add that in 0 to 4, but all you get is 1 lambda here. Your next bypass goes from 2 to 2, so that's a self loop on this state 2, and it's concatenating B with A, so you label that BA. And then your last bypass is 2 to 4, and you put that in, and you label it with the concatenation of B and lambda. We did not have any self loop here on 1 this time, like we did over here when we did it our different way on that other page. We did not have that this time. So this was the machine that resulted, and then you had to keep going, so then you blew up state 2. And when you did that, you had 1 incoming, 1 outgoing. This was the doodle that got produced, this one right here. This was the doodle. You had 1 incoming from state 0 to 2, labeled A. You had 1 outgoing from 2 to 4, labeled B. But then on state 2, the state you're getting ready to blow up, you have this self loop labeled BA right here. So taking out state 2 just left you with 0. Oh, that looks like an except state. Hold on. That just left you, whoops, interesting. I didn't know that happened. All right, so it left you, I'm going to do it up here. After you took out state 2, you're going to blow up state 2, all the roads except for the one road that went from 0 to 4 were getting blown up. So here's what you were left with after you blew up state 2. You had this with a lambda right there. Then you have to add this bypass going from 0 to 4. Well, you have a road going from 0 to 4. This is one of those cases where if you already have a road going from a place to a place and you're going to add another one, you want to put an OR between those. So we're going to, in our new machine, we're going to have lambda or what we're making from this bypass is A followed by BA star, because that's the loop, BA star followed by B. That bypass gets added to our existing transportation network. We already had a road from 0 to 4. It was labeled lambda. Now we add OR this business. And so we end up with this as our resulting regular expression. Whereas if we had blown up state 2 first, we would end up with the one we had when we did it before, which was quantity AB star. All right, now let me open up page 7 here. And we'll minimize this. And oh, here's me in my hat. Look at that. I love that hat. I was in Canada and I bought that hat. My friend who was with me took that picture. All right, so here, we're going to try this. Let me hide the hat. It's disruptive. Uh-oh. My great mouse skills. Okay. We're going to try this machine, starting from scratch. All right, this will be fun. I haven't done this in a while. Because as I said in one of these videos, it's been a couple years since I've even taught this algorithm. All right. So look, we have start state 1. I want to add a new start state. I'll call it 0. And I will lambda over to state 1, which was my original start state. And then I will have the rest of that. However, I have 3 accept states, 1, 2, and 3, and each one of them is going to lose its accept state status, and I'm going to add a new accept state 4. Oh, I guess I could call it 5. But remember, we're eliminating traps, so this is going to go away. I don't need that anymore, so I can call it 4. Here's my new accept state 4, and I'm going to have a lambda down to 4 from each of my original accept states. This is just getting me started before I start dropping bombs. Okay, now I need to put in all the other stuff. Don't leave any out. It's easy to leave something out. I've got a self loop on 1. I've got an edge from 1 to 2 labeled A, an edge from 2 to 1 labeled B, an edge from 2 to 3 labeled A, and an edge from 3 to 1 labeled B. Okay, so now we don't want to blow up 0 or 4 ever. They're going to be there at the end. That's all that's going to be there at the end. But which one do we blow up first, 1, 2, or 3? Well, we have to do our busyness calculation. So count edges that are coming in to 1. And don't count any self loops, just coming in from other places. We've got this one, that's 1. We've got this one, that's 2. And we've got this one, that's 3. So 1 has 3 incomings, and it has, I'll change colors here. It has this one and this one for outgoings. So that's 2. 3 times 2 gives me a busyness quotient of 6 for state 1. Now state 2, incomings come from 1, and that's it. So it has 1 incoming times, for outgoings, it has this one, and this one, and this one, times 3 equals 3. So that one's got a busyness quotient of 3. State 3 for incomings has just 1, and for outgoings it has 2. This one and this one. So 1 times 2 is 2. I'm going to blow up state 3. So let me drop my target, or lay my target down there on that picture. So here's my target. I'll do that one in green. I will draw a target going through any edges that go to or from state 3. Those edges are going to get blown up. Now let me make my doodle. I have to pair up each incoming with each outgoing. So here's 3 in the middle. I have 1 incoming from state 2. This busyness quotient, by the way, that's how many bypasses you're going to need. So I have an edge coming from 2, and I will pair it up with the one going to 1 first, and then my second bypass will come from 2 and go to 4. And there is no self loop on 3, so let me just label these. This road from 2 to 3 is labeled A. This road from 3 to 1 is labeled B, and this road from 3 to 4 is labeled lambda. All right, so now I redraw my transportation network, leaving out state 3. So I will have state 0. Oh, my phone is ringing. Let me pause this Panopto. Okay, I'm back. All right, so what were we doing? We were redrawing this machine without state 3. All right, so from 0 to 1, we have a lambda. There's a self loop on 1 labeled B. There's a state 2, and we have an A road an A road going from 1 to 2, and then a B road going from 2 to 1. Those aren't getting blown up. Then we have state 4 down here. And we have a lambda from 1 to 4. And we have a lambda from 2 to 4. All right, so our little transportation network has shrunk a bit, but we're not finished. We have to put in these bypasses. So this one goes from 2 to 1. From 2 to 1. Now we already have a B going from 2 to 1. We don't want to lose that, so we have to add B or, and this is AB. So this little part right here is going to change. It's not going to be just B anymore. It's going to be B or AB. B or AB. All right. That doesn't look too readable, but I'll try to remember what that was. Now we have to build another bypass that goes from 2 to 4. We already have one. It says lambda. Now we're going to have to add or, and when we concatenate these, we only get the A. We don't need that lambda since there's the A. So lambda or A is this road. And this is B or AB. We have to keep going until all that's left is state 0 and state 4. So we have to calculate again which one should we blow up next. Let's do our little busyness quotient. We don't count this self loop for 1. We only count incomings from other places, and there are 2 of them. So there's 1 and this one 2. 2 of those times there's 2 outgoings. 1 there, 1 here. 2 times 2. So the busyness quotient there is 4. That's how many bypasses we would have to build. Now for 2, we have 1 incoming times these 2 outgoings. 1 times 2 is 2. So we're going to blow up state 2 because we'll end up with a better regular expression if we do that. So here, let's draw our target. State 2 is going away, and so are these 3 roads. And all we're going to be left with then, oh wait, I got to do the doodle. Okay, so I did my doodle green before I do it green again. So my doodle has 2 in the middle, and there's 1 incoming from state 1, and there's 2 outgoings, 1 to 1, and the other one goes to 4. And there's no loop on 2. So just label these pieces. From 1 to 2, you get an A. So you got an A there, you got an A there. From 2 to 1, you've got a B or AB. From 2 to 4, you've got lambda or A. Okay. So now let's redraw our transportation network without state 2. We'll put all the roads in that exist right now, and then we'll add the bypass. So the roads that exist right now are 0 to 1, labeled lambda, self loop on 1, labeled B. We're leaving out 2. We have a 4 down here. And the edge to 4 is labeled lambda. But now we have to build our bypasses in. This bypass from 1 to 1, we already have a loop from 1 to 1. So now we're going to have to relabel this. Let me erase that B because I got to move it a little bit. It used to say B. Now it's going to say B or the concatenation of A with this quantity. So it's going to say B or A followed by B or AB. That came from the concatenation of these 2 pieces right here. And there's another bypass from 1 to 4. We have an edge from 1 to 4 labeled lambda, but we have to OR that with this, which is A followed by lambda, or A. When you get down to this point in this algorithm where you have only one state left to blow up, you can sort of see what's happening. I don't mean sort of, you can really see what's happening. And you don't really have to go through the process of blowing this state up, because the resulting regular expression is going to be the concatenation of this lambda with this loop starred, this whole thing starred, followed by that. All right, so this lambda we can do away with because it's not going to be necessary anymore once we have the rest of the expression. Let me show you what I'm talking about. All right, so we need the loop B or A followed by B or AB. That entire thing starred. That's from here. It doesn't help us to put lambda right there, because lambda is getting concatenated to this, and so that doesn't add any information to our regular expression. So we'll not use that. But then after this starred piece, we need this whole thing, and this lambda is actually essential to leave in, because that's saying you don't have to have anything more. You can have nothing more, or you could have an A followed by nothing or another A. All right, so actually what you could do, just using your human intelligence, is turn this into lambda or AA. That's the same thing. Lambda or an A followed by a lambda is just an A. An A followed by an A is an AA. So actually you could rewrite this part right here as this, and you do need the parentheses, because once you get to here, you either take nothing, or you take an A, or you take an AA. So this entire thing right here is the regular expression that came out of the machine that we are currently working on. I don't know that there was another machine to practice on, was there? Page 8 for me. Oh yeah, there's one more. Well, I will run through this, but since you don't really have to even learn this algorithm, unless you're vastly interested in this, you can just stop watching this video. But in case I do have some folks out there that want to see this, let me just do it. I need a new start state. I will call it, I already have a 0. I'll call it a 3. This is my new start state. And I'm going to lambda from there to my original start state of 0. And then I'm going to put in all the rest of the machine except take away the accept status of state 2, because I'm going to have a lambda from state 2 to my single accept state, which I will call 4 because I already used 3 out here. All right, so now let me put in the stuff that I don't want to omit. All right, so that's my machine. After I've added my new start state, my new accept state, at the end I'll have one edge from 3 to 4, and that'll have my regular expression written on it. So now let me calculate my busynesses. This state 0 has 2 incomings, one from 3, one from 2. Remember, you ignore self loops. And it has 1 outgoing, so it has 2 times 1 equals 2. This state 1 has 1 incoming, 1 outgoing, so you get 1 times 1 equals 1. That looks like a plus. It's supposed to be a times. And then this one has 1 incoming, 2 outgoing, so it's 1 times 2 equals 2. So clearly state 1 is the target. So let me draw my target around state 1, and I will make my little doodle. I only need one bypass. So it's going to go from 0 to 1 and then out to 2. And there is a loop on 1. I don't want to forget that. So make a little loop in your picture and label it with a B. You've got a B from 0 to 1. You got an A from 1 to 2. Redraw your machine without the state that you are blowing up. That would be 1. So we will have 3, 0. That's the lambda. We have a loop on 0 labeled A. State 1 is gone along with its roads. We have a 2 and we have a 4. Put in the lambda from 2 to 4. Put in the loop on 2. That didn't get blown up. But all those, oh, and put in the road from 2 to 0 labeled B. That didn't get blown up either. But these roads in here did get blown up. So now you have to build a bypass, and it goes from 0 to 2. 0 to 2. And it will be labeled B, B star, A. B, B star, A. All right, ready for the next pass. Calculate busyness. This one has 2 incomings times 1 outgoing. And this one has 1 incoming times 2 outgoing. So it's a tie. When it's a tie, you just randomly have to pick one. And the regular expression might be different depending on which one you pick. But you got to do something, so let's just pick this one. Okay, so my doodle. For blowing up state 0, we have 2 incomings. 1 from 3 goes through 0, and 1 from 2. And then we have only 1 outgoing, and that has to be paired up with each of these, so they go to state 2. The only outgoing I have. And there is a loop on state 0 labeled A. Don't forget that. The label from 3 to 0 is lambda. From 2 to 0 is B. From 0 to 2 is B, B star, A. And I put that here and here. All right, now let me redraw my machine. If I can find my cursor, I will scroll. I lose that blasted thing. Oh, here we go. Okay, so redraw the machine without state 0. So we'll have 3, 2, and 4. Put in the edges that didn't get blown up. That would only be this loop on 2 with an A on it, and this transition of 4 with a lambda. All those other roads got blown up. All right, so now I put in my bypass. The first one goes from 3 to 2. So here. And it is labeled with the concatenation of lambda, A star, and the rest of that. So the lambda goes away since it's getting concatenated. It's not ORed, it's concatenated. And I have A star, because it's a loop, and then B, B star, A. The other bypass goes from 2 back to 2. I already have a 2 to 2 with an A, so I have to OR this other piece, which is B followed by this loop. Remember, this loop is down here also. A star, B, A star, B, B star, A. All right, so now we're at that place where I can sort of see what's happening. This regular expression that's going to get produced is going to say A star, B, B star, A, then the quantity A or B, A star, B, B star, A, whole thing, starred, and then this lambda is not necessary. It's getting concatenated onto the end here, so you can leave that off. That is your regular expression that comes out of this algorithm for this machine. Where did my machine go? Let's go look at it. For that machine up there. So let's see if it makes sense. I can copy and paste. Select rectangular. I want to select this guy and paste this right up here. All right, so does this make sense? I'm thinking that this part out to, let me have a color, out to, sorry, not a fan of pink, out to right here, that's all that's mandatory. This part out here is optional with a star. You don't have to have it. You can have it if you want it, but you don't have to. So this part right here, it ought to get me to an accept state. So let's see, A star, and then a B, and then a B star, and then an A, and I get to this accept state. And that's right. So right to here gets you to the accept state. This out here, I'm thinking, is two ways to leave the accept state and come back. Either that or this. Does that make sense? Yes, it does. Because look, you can leave and come back with that, A. Or you can leave with B, A star, B, B star, A, and come back. And you can do the A loop as many times as you want, including none. You can do that big old loop as many times as you want, including none. But both ways will get you back to an accept state. All right, I believe since this says one last example, we are finished talking about the optional algorithm that we call NFA to REX. Thank you.